Particularly in coordination number 4 complex, there are two types of geometries are possible. One is square planar geometry, another is tetrahedral geometry. So tetrahedral geometry particularly favorable in these particular cases when the ligand size is bigger or the ligand size is bulky. But in case of the less steric ligands, we can prefer the square planar complexes because in tetrahedral complex, if you compare the bond angle is 109 degree and in square planar complex the bond angle is 90 degree. That means in square planar complexes, the ligands are closely occupy its position, and in tetrahedral complexes, the ligands are far away from each other due to its larger bond angle. That's why the bulky ligands it will prefer the tetrahedral geometry, and the less bulky ligands it will prefer the square planar geometry. Or in other sense, we can say a tetrahedral geometry is sterically stable. Sterically stable. That means it can occupy the bulky ligands. And a square planar complex is energetically or according to ligand field stabilization energy, a square planar geometry is stable. That means in square planar geometry, the ligands are close to occupy its position, and this closely occupied position is due to its a higher binding nature of metal with the ligand. So in graduation also, you know about the crystal field stabilization energy. So in between tetrahedral complex and square planar complex, the square planar complex has larger stabilization energy or larger crystal field stabilization energy. That means in square planar complex, the metal ligand binding tendency is very high. So in square planar complex, maybe the ligands closely occupy its position, but it is tightly bound with the metal. Okay, so preferably D9 and D8 electronic configurations, it will form the square planar geometry. So particularly these types of metals, nickel 2 plus, palladium 2 plus, platinum 2 plus, rhodium plus 1, these D8 electronic configurations form the square planar complexes. But out of all these metals, particularly platinum, form mostly the 80% of the square planar complexes. Due to some particular reason, first one is that the platinum plus 2 complexes are very stable. Second thing, it is very easy to synthesize. Okay, so unlike other complexes, the substitution reaction in platinum undergoes a slow rate. So when a formation of a compound undergoes a slow rate, you can easily analyze every step of the reactions. Okay, so the slow step it is good for chemical kinetics. You can measure easily the rate of the reactions. So other reactions or other metal complexes, particularly in nickel plus 2 and palladium plus 2, the square planar complexes undergoes 10 to the power 6, 10 to the power 7 times more rapidly than the platinum. So it is very difficult to analyze the reactions of nickel plus 2 and palladium plus 2 comparing to the platinum plus 2. So why? There may be a rise of a question why platinum plus 2 complexes form mostly the square planar complexes. Mostly first reason is that it is very stable. The platinum complexes are very stable due to the 5d orbital. Second thing is it is easy to synthesize, and the third thing is that the reaction substitution reaction rate is very slow, so you can easily analyze the every step of the reaction. Next, we will discuss about the mechanism of the square planar complexes. So, in particularly square planar complex, they will follow mostly the associative mechanism. In octahedral complexes, they will follow mostly the dissociative mechanism or SN1 mechanism, and here will it can follow the SN2, mostly the SN2 mechanism. And along with, we'll discuss details about how it can perform the SN2 mechanism. But initially, we just need to remember square planar complexes prefer SN2 and octahedral prefer SN1 or dissociative mechanism. Another thing is that in square planar complex, when the substitution reaction occurs, there will be a retention of configuration. That means if the initial reactant is cis complex, then the final product will be also cis. If the initial reactant is trans, and the final product will be trans. That means we can say in substitution reaction, square planar complexes favor the retention of configuration. Okay, you can read out here. Okay. What are the other factors that will affect the substitution reactions in square planar complex? The first thing is that nature of entering ligand. So there are several factors. You can remember one by one. The first factor will be the nature of entering ligands. That means the incoming ligand's nature. So particularly when a incoming ligand, it will attach with a metal complex. The nucleophilicity will be the most important factor, and along with nucleophilicity, the metal and sorry the incoming ligand, it possesses some basicity nature. So there will be a difference in between basicity and nucleophilicity. But the most necessary thing is that nucleophilicity of the incoming ligand, it should be very good for formation of a metal complex or for the formation of a associative complex. So particularly he's saying that according to hard soft acid base mechanism, particularly the polarizable groups, it will interact with the metal complexes. That means soft groups, or I can say highly polarized ligands, it can prefer to the metal complex, because in square planar complexes, particularly the platinum will form the complex, and the platinum atmosphere is just like a soft atmosphere, or I can say platinum plus 2 is a soft metal or it is a soft substrate. That's why it will prefer always the more polarizable groups. That means which are the soft ligands. So you can see here there are few examples of the ligands. Okay, the order of the ligands. Out of these, all the ligands, these ligands are 3p. Okay, it may be triphenyl phosphine or it may be trialkyl phosphorus, and Tu just like thiourea, iodine minus, ACN minus. These are the soft ligands. Okay, so with the soft ligands, the rate of substitution will be higher, and these hard ligands, it will lie on the low end of the order. That means with these soft ligands, the rate of the reaction will be higher. What is the reason? The reason is that platinum plus 2 or other substances also you can check, other metal configuration you can check, palladium plus 2, rhodium plus 1, they will also form the soft environment, or they will just behave like a soft metal. That's why they will prefer the soft ligands, or I can say the highly polarizable ligands. Okay, so out of this all the ligands, these ligands at the end of these ligands are 3p, Tu, I minus, Sn minus, N3 minus. In case of these ligands, the rate of the substitution reaction will be higher. And another thing is that nucleophilicity. More is the nucleophilicity of the entering ligand, and higher will be the rate of substitution reaction in associative mechanism. Okay. And another factor is that nature of the leaving group. What will be the nature of the leaving group? Here you can see here experimental data of a living group nature. These are the living groups, and the incoming ligand is the pyridine. I am taking platinum diene X. Diene means this is a tridental ligand, and X, it will just behave like a monodental ligand. That means this complex is a four coordinated square planar complex. It will interact with the pyridine, then it will form a complex like that. The X will be the living group. So out of all these ligands or living groups, NO3 minus cases or water cases, the rate of substitution reaction will be faster. Okay, so this is the experimental data or experimental rate constant value. You can remember this order. So NO3 minus will be at the higher end. That means in case of NO3 minus living group, the rate of the reaction will be rate of substitution reaction, it will be faster. And another thing is that charge effect. We will previously in previous class we will discuss about the charge effect. In charge effect, we will discuss that if the metal complex's charge is very less, then it can do substitution reaction in a faster way. Or if the metal complex's charge is very high, then it can do the substitution reaction in a slower rate. But here we are taking four different complexes having four different charge atmosphere. Here the charge amount is 2 minus, here the charge amount is minus, here it is 0, it is plus. That means the charge varying from minus 2 to plus 1. Okay, but when we will observe the substitution reaction rate of these four complexes, we get that the rate constant value of these four, are different, but there will be very less difference in the rate constant of these four complexes, because these four complexes will pass through a associative mechanism. If it will pass through a dissociative mechanism, then definitely effect will be a major effect. But mostly the square planar complexes, it will pass through a dissociative mechanism. You can read out here. There is a larger difference in charges, but there will be very remarkable small variation in rates. Yes or no? And the platinum chlorine bond breaking should be more difficult in complexes with higher positive charge. That means in higher positive cases, the platinum chlorine breaking should be very difficult, and in lower positive charge cases, the platinum chlorine breaking should be very easy. But here, the rate constant value is almost equal. That means here the platinum chlorine bond breaking is not a major factor. That means in the rate determining step, there will be an association of a incoming ligand. There will be no dissociation of a platinum chlorine bond in the rate determining step. So here in associative mechanism, it's important to form a bond with the new incoming ligand rather than the breaking of the platinum and the leaving group bond. So you can read out here. That means this discussion indicates that platinum chlorine bond breaking and platinum OH2 bond, whatever may be the leaving group OH2 or chlorine bond making, both are of equal importance, and the reaction proceeds by the associative mechanism or it may be interchange associative mechanism. Okay, but it's not following any dissociative path. Okay, when it will follow some dissociative path, then this leaving groups bond with the metal, or I can see the metal bond strength of the metal with the leaving group. It will be the major factor. Okay, so here different charge complexes are present, but the chemical rate constant of different complexes are different. But the difference in the rate constant, it will be very less. And another factor is that steric effect of the non-living ligands, or I can say the spectator ligands, that will participate in the non-living ligands means that will participate in the reaction, but it cannot remove from the complex. Okay. So in previous class also we will discuss that in dissociative mechanism, the spectator ligands, if the spectator ligand will be bulky, then the dissociation will be much more favorable. That means in the first step we are making the separation of leaving group from the metal complex. If the other ligands present in the metal complex, it will be bulky, then definitely the leaving group it can easily remove from the complex. Okay, that means it will favor the dissociative pathway. That means the spectator ligands bulkiness or steric effect, it will favor the dissociative pathway. But when a metal complex follows a associative pathway, if the steric hindrance present inside the complex, then the rate of the substitution reaction will decreases. That means steric effect of the spectator ligand, it is favorable for the SN1 mechanism. That means if the complexes have more steric effect, if the spectator ligand of the metal complexes have more steric effect, then SN1 mechanism will be faster. If the metal complexes of the spectator ligand of the metal complexes have much more steric effect, then the rate of the reaction will be slower in case of SN2 mechanism. That means steric effect is good for SN1 mechanism and it will be bad for the SN2 mechanism. Here you can check some data of the rate constant. Here taking one cis complex and trans complex. You can check any linear data also. Okay. In case of pyridine, the value will be 8 multiplied 10 to the power minus 2. If you put one methyl group in the chain of the pyridine, the rate will be 2.0 10 to the power minus 4. That means the rate constant decreases. If you put another methyl group, then the rate will further decreases. Sorry, the rate will be further increases. You can check here. Sorry, decreases. That means it is following the dissociative path. This value will be larger, this value will be smaller, this will be much more smaller. That means with increase in steric hindrance, the SN2 rate it will decreases. If the reaction will follow the SN1 mechanism, then with increase in steric hindrance, the rate will increases. Here it will following the SN2 mechanism. That's why the rate will decreases. So in case of pyridine, the rate value will be highest. In case of 2-methylpyridine, the rate will be little bit lower. And in case of 2,6-dimethylpyridine, it will be the lowest. Okay. Next most important effect is that solvent effect. Okay. So in square planar complexes, mostly you are using the solvents that has good coordinating tendency. That has good coordinating tendency along with the metal. That means that can interact easily with the metal complex. That can easily donate its electron density towards the metal complexes. That means the solvent must have a good coordinating tendency. Here you can read out these things. The good coordinating solvents like DMSO, dimethyl sulfur oxide, water, and alcohols, etc., provide almost entirely solvent path exchange. Okay, so these solvents are good for this in SN2 mechanism in square planar complexes. You can remember this order. DMSO, it will be much more favorable for associative mechanism in square planar complexes. The rate of exchange is faster in case of DMSO. So mostly water, alcohol, and DMSO you can use as a solvent in square planar complexes. You can check the experimental data. That means in DMSO, the oxygen is present and the oxygen atom it can coordinate with the metal complex. In water molecule, this oxygen can coordinate with the metal complex, and this alcohol also this oxygen can coordinate with the metal complex, having lone pair of electron. But if you take these types of non-polar solvent just like CCl4, there will be no any atom that can easily coordinate with the metal. You can take benzene, no any atom that can donate its lone pair to the metal coordinating with the metal complexes. So these are act as just like poor coordinating ligands. So these are not favorable for the square planar mechanism in square planar mechanism complexes or square planar complexes or the complexes that follow the associative pathway. Okay. The second another factor is the trans effect. The trans effect is the one of the most important effect. Most of the time, the question will come from this effect, trans effect. So trans effect is a kinetic factor. It is not a thermodynamic factor. That means when we are discussing about the ligand exchange rate, that means that we are discussing about the kinetic stability. So trans effect is a first thing is that it is a kinetic phenomenon. It is a kinetic phenomenon. Okay. So ligands other than the entering and leaving groups may affect the rate of substitution reaction, and the ligands which is not lost in the reaction is called a spectator ligand. We already told that. Okay. And the postulate saying that the effect of a spectator ligand coordinated to a metal cation upon the rate of substitution reaction, ligand trans to its trans effect. That means he is saying that in a metal complex, a spectator ligand is present, and this spectator ligand it will decide which group will remove from the metal complex and in which position the incoming ligand it will attach to the metal complex. This is the role of trans effect or trans directing ligands. That means here we can check one of the example also. We are taking this complex MLXX. Okay, in which L is a spectator ligand. We can consider L is a spectator and non-living ligands. And out of these three ligands, X, one can be act as a living group. Yes or no? You can read out here. You can read out these things. If the ligand X trans to ligand L. So out of these three ligands, three are possible living groups. Which ligand will remove from the complex? The ligand which is present trans to the spectator ligand. So here L it will decide out of these three living groups which will eliminate from the metal complex. So this ligand that removes the living group which is present in opposite position or trans position of the spectator ligand, this is called trans directing ligands. This is called trans directing ligands. That means it has more labile effect. That means the presence of the spectator ligand, it increases the labileness of this leaving group or the removal tendency of this group. Here you can read out L is said to have a larger labilizing effect or translabile effect. Since L makes the ligand X labile, that means L it will makes the ligand labile. That means this MX bond weaker. So the spectator ligand or labile trans effect of the L ligand, it will make this MX bond weaker. Then the X will remove from the complex, and the incoming group again it will come and it will attach with the metal complex in this direction. Yes or no? So this is the order or trend of a trans effect. Okay, you can see here at high end we can check here cyanides, CO, NO, C2S4, PR3, arsenic R3, H minus. These types of ligands are present. So mostly you can see here the pi acceptor ligands have a stronger transdirecting tendency, just like Cn minus, CO, NO, just like that. And the pi donor ligands, just like chlorine minus, OH minus, water, it has a lowest trans effect. So you can just remember this trend. Otherwise, you can just consider that whenever there is the presence of pi acceptor ligand, definitely it is a strong transdirecting effect. Okay, whenever there is the presence of pi donor ligand, definitely it has a lowest trans effect. And in between the middle of the trend, there will be presence of sigma donor ligands. H minus, CH3 minus, just like that. C6H5 minus. Okay, so there will be another term. This is called trans influence, and this term is called trans effect. So trans effect is a kinetic term, and the trans influence is a thermodynamic term. So trans, when I'm discussing about trans influence, we need to check particularly the metal bond length. And out of these three cases, you can see here this platinum chlorine metal bond length is bigger. That means this bond is weaker due to presence of the spectator ligand triethyl phosphorus, which is larger trans effect that makes this bond weaker. So this removal of chlorine from this metal complex, it will be easier. Okay, but when we'll discuss about the question, they will ask from trans influence. There will be separate order of trans influence also. So the trans influence is governed by the thermodynamic parameter, and the trans effect is governed by the kinetic parameter. Then we'll discuss about the application of trans effect by using trans effect, how you can form different types of coordinate complexes. Okay, the first one is the formation of cis platin. This complex is called cisplatin. This is called cancer anti-tumor agent. That means in cancer treatment, one NH3 ligand. Then in second step, we'll check in which axis the labile effect is more. Which axis means we can consider this axis, we can consider this axis. So tell me, in this axis, which ligands are present? NH3 is present and Cl is present. And in this axis, which ligand is present? Cl is present and Cl is present. So tell me, out of NH3 and Cl, post trans effect is more. You can check here trans effect of NH3 and then trans effect of Cl. Post trans effect is more, Cl minus. And ammonia trans effect is less comparing to Cl. That means in this direction, there will be more labile effect or there will be more trans effect. But in this direction, One chlorine is present, one ammonia is present in this axis. So the labile effect will be more in this direction or in this axis. And here the labile effect will be less due to presence of one chlorine and one NH3 ligand. So in the second step, the leaving of the group, there will be removal of the ligand occurs from the this axis. In which axis the labile effect is more. So out of these two chlorines, one So in this way, we are forming the cisplatin complex. Now we can check how can we are forming the trans complex. Okay, so to form a transplatin, we need to take this tetraamine platinum complex in the first step. Then we are adding one chlorine minus anionic ligand. So it can replace any ammonia from this metal complex and it will form a complex like that. Okay, now we need to check in which axis particularly there will more labile effect. Here you can see in this axis the two ammonia are present. Amine group are present. One is NH3, one is NH3. And in this axis, two, one amine, one chlorine is present. Then tell me in which axis. If I say this one will be the right hand side axis, this one will be the left hand side axis. In which axis there will be more labile effect. This one will be right hand side, this one will be left hand side. Can anyone say in which axis there will be more labile effect? In this axis, two amine group is present. You know that the trans effect of the chlorine is much more than the amine group. So in this axis, presence of one chlorine along with the amine group, and in this axis, presence of two amine group. So we can say in this axis, there will be more labile effect. There will be more labile effect. But if you compare in this axis out of chlorine and ammonia, which is more labile effect or which is more trans effect? So particularly Cl has more labile effect. That's why Cl cannot act as a leaving group. And here the ammonia will act as a leaving group. So ammonia will remove the second step and the chlorine will attach in this direction. That means this chlorine, it will decide The incoming ligand, the incoming ligand will occupy which position. So due to this presence of chlorine, due to this presence of the higher trans effect ligand, this will make the platinum ammonia bond or amine group bond it will weaker. Then this NH3 it will act just like a leaving group. It will be removed from the complex and the chlorine will attach to the site. So here you can form the trans complex like that. Okay. So you can also practice some other examples. How can you synthesize cis and trans platinum NH3 NO2 Cl2 minus ion? Okay. So here you can say there are three types of ligands are present, four number of ligands are present. That means it is a tetracoordinate complex. We will discuss only about the square planar complexes. So out of these three ligands, NO2 minus has highest trans effect, then chlorine minus, then NH3. That means NH3 has lowest trans effect. So before going to synthesis process, you need to remember this trend. So this trend is coming from this one. Okay, so this order is very important. We need to remember this trans effect order. In first case, we are forming this cis complex. So to form this cis complex, we need to take this initial reactant platinum Cl4 2 minus. We are adding ammonia, and this ammonia will occupy any of the chlorine position. This complex will be like that. And in second case, we need to check in which axis there will be presence of more labile effect. We can check this. We can check this axis. So in this axis, one NH3 chlorine is present, and in this axis, two chlorine is present. So definitely chlorine has a larger trans effect. So in this axis will act like a more labeling axis. So out of these two chlorine atom, one of the chlorine atom will remove from the complex. And there will be addition of NO2 minus ligand. So uh, the removal of chlorine it can occur from this side also, or it can occur from this side also, from any direction. But it will definitely form a cis complex. Okay. So here you are removing this chlorine atom. We are adding NO2 minus in this direction. So we are forming this cis complex. And how can you synthesize this trans one? Initially, we are taking the same reacting complex, but initially we are adding the NO2 minus. So after addition of NO2 minus, this complex will be like that. Now you need to check in which direction there will be presence of more labile effect. In this direction, chlorine is present, but in this direction, along with chlorine, there will be one NO2 minus ligand. And you know that the NO2 minus ligand has higher trans effect compared to chlorine, NH3. So from this axis, there will be a removal of a ligand. So out of these two ligands, chlorine and NO2, NO2 has highest trans effect. So it will behave like a trans-directing ligand. Into chlorine and NH. So if you can understood these two things, two steps synthesis, you can also do this one very easy. So these are synthesis method you can practice also that are also available in your study material. So there will another test. It's called Kunnakov test, or you can read out the scientist name Kunnakov, particularly called Kunnakov test. And by using this test, you can Distinguish between cis and trans isomer of platinum complexes. You can distinguish the cis and trans isomer. So in Kornakov test, we are using TU ligand. TU ligand means thiourea ligand, and the representation of thiourea is chemical formula of thiourea is NH2CsNH2. Yes or no? Suppose we are taking initially a cis isomer complex, and you are adding 2 moles of thiourea. You are adding 2 moles of thiourea. Why we are adding 2 moles, not 1 mole? Because if you compare these two axes, here also and here also, similar types of ligands are present in this axis. One ammonia, one chlorine. In this axis also, one ammonia, one chlorine. So the two axes have similar labile effect. The two axes have similar labile effect. And out of these two ligands, in this axis also or in this axis also, the chlorine has the highest trans effect comparing to ammonia. That means chlorine will act just like a trans-directing ligand, and NH3 will act like just like a leaving group. So you can write also two steps, but in one step you can represent. You can also represent in one step. So you are adding 2 moles of thiourea, and here the ammonia gas or NH3 amine complex, it will act just like a leaving group. So NH3 will remove from the complex, and this 2Tu group, it will attach to the metal complex like that. And in next step, after the addition of 2 moles of thiourea, we are adding further 2 moles of thiourea. So before addition, you need to check the labile effect of different axes. You can check this axis, you can check this axis. Here also in two axes, it has same labile effect. It has same labile effect. But the difference is that here thiourea is present, in previous case ammonia is present. So you compare any one axis, thiourea out of thiourea and chlorine, which is more trans effect. Thiourea has more trans effect. You can check here from the order. Thiourea, CS, NH2, NH2. This one comparing to chlorine and ammonia. So thiourea has more trans effect. So out of these two ligands, thiourea, it will act like a trans-directing ligands, and the chlorine will act just like a leaving group. Okay. Out of these two ligands, thiourea will act just like a trans-directing ligand, and this chlorine will act just like a leaving group. So after addition of two thiourea, this chlorine will remove from the complex, and this chlorine will also remove from this complex. So there will be a formation of these types of complex. Okay, so the test predicts that if this initial complex will be cis, then the product will be like that. If the initial complex will be trans, then in first step you can add one thiourea. Why you are not adding 2 moles of thiourea directly? Because in previous case, in two axes, the environment is similar. But here, in these two axes, the environment is not similar. So you can add one by one thiourea. Okay. So before addition of one thiourea, you need to check the labile effect. You can check in this direction also. You can check in this direction also. So in this direction, two ammonia groups are present, and in this direction, two chlorine groups are present. Then definitely in this axis, in which axis the labile effect will be more? In this axis, because chlorine has larger trans effect than the NH3 group. So one of the chlorine, it will be replaced by one TU group or thiourea group. The complex will be like that. But in next step, when you are going to add further one mole of thiourea, again you need to check this axis and this axis, and you find that in this axis there will be more labile effect, and out of TU group and Cl group, TU has larger trans effect. So here the chlorine will behave like a leaving group. So you can form the complex like that. So one can answer after the formation of this question, that after the formation of this complex, why we are not adding further TU groups, or why we are not adding further thiourea groups. If you add further thiourea, then definitely it will remove one thiourea and it will attach another thiourea at particular this place. That means we are forming this similarly same complex. Okay, because if you compare this complex, if you see carefully this complex, you can check this axis, you can check this axis. So definitely in this axis, the labile effect will be more. So out of this two TU group, definitely one TU will remove from the complex and another TU will be added to the complex. That means you are just removing one TU, you are just adding one TU. That means you are forming the same complex. So we can stop the reaction here. We cannot further add more TU groups. But in the initial complex, cis complex, you can add up to 4 moles of TU or thiourea ligand. But here you can add up to 2 moles of thiourea, because you can, if you add further one more TU or many more moles of TU, then definitely you are forming the same complex. The same complex in formation of which formation of. So in cis complex, it will form these types of complex. In trans complex, this will form the resultant product will be these types of complex. So you can definitely distinguish if these types of platinum complex are forming, then definitely the initial one will be cis isomer, and these types of platinum complex is forming, then definitely the initial complex will be trans isomer. So this test is very important. They can ask question also. How can you distinguish in between cis and trans isomer? Kurnikov test and different other types of tests are also known, Greenberg test, but this one is much more important. Okay, next we will discuss about the theories of transcript. Okay, or I can say particularly the mechanism of transcript, how this living groups are removing from the complex, how another group are attaching to the metal complex. And the first one will be the polarization theory. Okay, and it was given by Greenberg in 1927. So in this complex particularly, he's saying that according to this theory, the larger trans effect of the L group means the spectator ligands, the ligands which is showing larger trans effect. It will particularly destabilizes the ground state energy. And the ground state energy of the particular ground state energy means it will destabilizes the metal and ligand bond. That means it is making the metal and living group bond weaker due to its high polarization nature, due to its high polarizability nature. That means, according to Greenberg, L or a larger transiting group has a more polarizable tendency, and due to this transiting group has more polarizability tendency, it can make weaker the respective metal living group bond. So, by using the charge concept, you can see check here. If your initial complex is platinum X4, then we can draw just like that. Here, there will be one ligand is present. So in all the four directions, same ligand is present. So if you are going to calculate the resultant dipole moment, then it will be zero. It will be zero, because in this direction, the attraction in this direction or electron shifting in this direction is cancelled by this direction. So the net dipole moment is zero. But if you are taking the platinum LX3 type ligand, and here L will be the transdirecting ligand. We can see here platinum LX3. That means here ligand L is present, here ligand X is present, and in this direction another ligand X is present, or in this direction another X ligand is present. That means in this axis, definitely the dipole moment will be zero, because the electronic attraction in this direction it will be cancelled by the electronic attraction in this direction. So we can say in this axis the net dipole moment is zero. But if you check this direction in this axis, there will be two different groups are present. One is L, another is X. That means X is the leaving group, L is the transdirecting group. So according to the Greenberg theory, is saying that if the transdirecting ligand L, it will be more polarizable. It will be more polarizable. It can make this platinum X bond weaker. It can make the platinum X bond weaker. So if you are taking a large polarizable groups of ligand, the negative charge of the ligand, it will attract more easily the platinum's positive charge towards itself. So the dipole arrangement, it will be just like that. Here you can see the negative charge of the larger polarizable groups. It can easily shifted the positive charge of the metal towards itself. That means the positive charges are shifted towards the more polarizable groups. And the negative dipole of the metal, it will attach with the another ligand, X minus. So here, this negative charge of this negative part of the metal complex or negative dipole of the metal complex, it will repel to the leaving group's negative charge, and it makes platinum X bond weaker. Yes or no? So according to this theory, if a transdirecting group will be more polarizable group, it can attract the positive part of the or positive dipole of the metal towards itself. The negative dipole of the metal, it will remain in the direction of the leaving group, and this negative dipole, it will repel the negative charge of the leaving group. That's why this platinum X bond, it will be weaker. It will gradually weaker. So it is favorable to remove from the complex. Then it can make a favorable condition that the X minus, it can easily remove from this complex. Yes or no? So according to Greenberg theory, if a transdirecting ligand has more polarizable nature, then it has more trans effect tendency. It has more trans effect tendency. So by using this first theory, we can say the more polarizable group has larger trans effect. Secondly, you can see the another theory. This is called pi bonding theory. Okay. So by using Greenberg theory, you can compare or you can predict that the groups or the ligands which is larger trans effect, definitely it is more polarizable nature. But all the ligands, that doesn't mean all the ligands must have higher polarizable nature. So by using Greenberg theory, you can certainly classify some of the ligands that it has larger trans effect, it is larger polarizable nature, it has lower trans effect, it is a lower polarizable nature. But in case of pi acceptor ligands, these are not polarizable groups, but it is very high trans effect. It is very high trans effect. So by using Greenberg theory, you can compare or you can give the trans effect order of these ligands, just like H minus, CH3 minus, C6H5 minus, iodine minus, bromine, chlorine up to water, up to from this one to this one. That means by using Greenberg theory, you can make the order of these groups. But you cannot predict the trans effect of the pi acceptor ligands. Okay. So by using Greenberg theory, you can predict the trans effect order of the sigma donor ligands and pi donor ligands. You cannot predict the trans effect order of the pi acceptor ligands. So to predict the trans effect order of the pi acceptor ligands, there will another theory. This is called pi bonding theory. Pi bonding theory. So finally, when we are studying the trans effect order, that means it is a combination of Greenberg theory and pi bonding theory. Okay. So according to Greenberg, definitely you can compare the ligands which is larger polarizable nature, it is large trans effect. The ligand which is less polarizable nature, it is less trans effect. But when you are comparing the pi acceptor ligand, the polarizability will be the not the major factor. Okay. So if I say pi acceptor ligands, then definitely you can imagine just like that. This is a metal. This is a pi acceptor ligand. First, the pi acceptor ligand will donate a pair of electron to metal to form a sigma bond. It will initially form a sigma bond, and in next step, the types of electrons. Metal donates the field d electrons. It donates its field d electrons towards the vacant orbital of ligand to form a pi bond. To form a pi bond. Okay. So which types of vacant orbitals that are available in pi acceptor ligands? In some cases, the vacant orbital will be pi star. You can see. In some cases, it will be the pi star orbital. Okay. Or in some other cases, it will be d pi orbital, or in some other cases, you can mostly check the antibonding orbitals. Suppose you are taking CO ligand, Cn minus ligand, C2H4. In these cases, the vacant orbital will be pi star. It will be pi star. Suppose you are taking R3P, trialkyl phosphorus. Here, the vacant orbital will be pi star orbital. Sorry, sigma star orbital. Okay. So mostly the d pi electron it will donate it towards the ligand's vacant orbital, and vacant orbital sometimes it can be a pi star orbital, or sometimes it can be a sigma star orbital. Okay, and these types of complexes, the metal has low oxidation state. That's why it can donate its electron towards the ligand vacant orbital. Okay, you can see here, read out these two sentences. If the ligand is CO, then the pi bond is formed by the donation of electron pair from the d orbital of platinum to the vacant pi star of CO. If the ligand is R3 free, then the pi bond is formed by the donation of electron from the d orbital to the vacant d orbital of phosphorus. Okay, or we can consider it's not particularly vacant d orbital of phosphorus. You can see here, say here, the sigma star orbital of phosphorus, because in R3P, particularly if you discuss about R3P, there will be no presence of sigma pi bond. There will be presence of sigma bond. So when the sigma bond is available, definitely its antibonding orbital sigma star is available. So when the interaction occurs from the metal to the phosphorus, it will the electron will donate towards the sigma star orbital of this ligand. Okay, so if when there will be pi acceptor ligand, the interaction may be d pi pi star, or the interaction may be d pi sigma star, and the d pi will be always from the metal side. Okay, you can see here this pi bonding interaction occurs in between d pi pi star, or d pi, or you can consider here d pi sigma star. D pi sigma star will be, and the sigma star orbital will be like that. The amplitude will be different. One will be positive, another will be negative. Okay. So whatever it may be, when there will be formation of pi bond, definitely there will be sideways overlapping of the orbitals. Okay. So what happens particularly after the interaction of pi bond? So when the pi bond interaction occurs, the metal will donate its electrons towards to the ligand. First it will form a sigma bond, then it will form a pi bond. So when there will be formation of pi bond occurs, the metal will donate its electron density towards the ligand. If metal will donate its electron density towards the ligand, then in the direction of leaving group direction, there will be less available of bonding electron of metal. That means metal donates its field bonding electron towards the ligand, and in this direction the bonding electron density will decreases. So when the bonding electron density will decreases in this direction, the bond length also decreases, and this bond will be weaker. Okay, if the electron density will be available in this direction, then the leaving group it can interact with the metal, it can form further bonds like that. But here, metal will donates its electron density towards the ligand. That means the bonding electron density will shift towards the spectator ligand. So in this direction, the bond strength will decreases. That means this metal and this leaving group bond strength decreases. It will become weaker. So this X bond, this MX bond, it can easily dissociate, and the X can remove easily from the complex. Okay, so you can check here also. Here you can check platinum L is the transdirecting ligand, and X is the leaving group. If electron density increases in this direction, then this platinum X bond length increases. That means this platinum X bond strength decreases, bond length increases, or we can say the platinum X bond strength decreases. Okay, so these are the two theories. One is pi bonding theory, another is Greenberg theory. So we can compare, or we can say by combining these two theories, we can predict a trans effect order. So in the trans effect order, mostly on the high end side, the strong pi acceptors are present. That means strong pi acceptor ligands has highest trans effect. Then sigma donor ligands, just like strong polarizable ligands. Okay, SN minus, I minus, H minus, CH3 minus. Then at the low end of the trans effect order, the pi donor ligands, just like water, OH minus, NH3, these are present. Yes or no? So you can make a check also on the trans effect order. This one. Okay, then we'll discuss about the mechanism of trans effect, or the mechanism of substitution reaction in square planar complexes. So the square planar complex, it is following the associative mechanism. You can see here, this is a square planar complex, this is the incoming ligand. In first the association occurs, it will form a pentacoordinated complex, platinum L A A X Y. And this square pyramidal geometry, this one, this will get rearranged to TPP geometry. It will get rearranged to TPP geometry. When there will be rearrangement occurs, there will be retention of configuration. Retention of configuration means here we can check L is nearer to X also, L is nearer to Y also. So in TPP geometry, we can say L is sees to the X also, and this A is sees to the Y also. That means when there will be rearrangement occurs, the bond angle will change, but the neighboring position it doesn't change. Here the A is nearer to X and Y. Here also A is nearer to X and Y. A is making 90° to X. Here also A is making 90° to Y. Yes or no? But what is the difference? In square pyramidal geometry, the XY bond angle will be 90, and in TPP geometry, the XY bond angle will be 120. And here you can check also, here L is nearer to A also. Okay, and here L is also nearer to A. Here you can check L is Cis to A also, L is Cis to A also. Okay, so the square pyramidal intermediate, it will rearranges to give a trigonal bipyramidal geometry like that. Okay. Further, this trigonal bipyramidal geometry, it will rearrange to give further another square pyramidal geometry. So in this geometry, on the axial position, there will be presence of the living group. But in the first square pyramidal geometry, in the axial position, there will be presence of the incoming ligand. You can check. The first square planar geometry, it will rearranges to give square pyramidal. Further, it will rearranges to give the trigonal bipyramidal geometry. Further, it will rearranges to give square pyramidal geometry. But in the initial square pyramidal geometry, in the axial position, there will be presence of incoming ligand. And in this square pyramidal geometry, there will be presence of, in the axial position, living group. In the next step, this X will be removed from the complex. They will form this square planar complex. Okay, that means simply in place of X, we are putting Y. Initially, AA is trans, and in the final product also, AA is trans. That means we can say there will be retention on confusion. Initial one will be the trans complex, and final one will be also the trans complex. We are just removing the X from this position. We are just adding the incoming ligand in this position. For the reaction, it will follows these types of rearrangement pathways. Square planar to square pyramidal, then trigonal bipyramidal, then further square pyramidal, and further square planar. Okay, you can check some other examples here also. The initial one will be the cis complex. A is cis to each other, and the final product will be also cis. A is cis to each other. Here also, the initial one is the trans complex, and the final product is also trans. So there is retention in configuration. Okay, and some other scientists tell that there will be no issue with the retention of configuration, but the reaction it can also follow the solvent pathway. Solvent pathway means initially the incoming ligand doesn't interact with the metal complex. Initially, the solvent it will interact with the metal complex. This pathway is the solvent pathway, and this pathway is the previous pathway. I already told you which one. Okay. Initially, the solvent will interact with the metal complex, and in the next step, in place of solvent, in the next step there will be removal of the living group. Okay, and it will form a square planar geometry like that. And in the second step, there will be addition of incoming ligand, and this incoming ligand, in the last step, it will just occupy the position of water, and they will form the similar product. In the previous pathway or in the solvent pathway, the product is similar, but the steps are different. In solvent pathway, in the first step, you are adding the solvent molecules. Solvent molecule will add to the complex. It will form a associative complex like that. There is a, and in the previous pathway also, they will form a associative complex. But the difference is that initially the incoming ligand act as a nucleophile, and in solvent pathway, solvent will act as a nucleophile. Then in second step, there will be removal of leaving group. It will form a square planar complex like that. And further, the next step, there will be removal of solvent molecule. There will be addition of the incoming ligand. So the two-path mechanism, sometimes it is told that the square planar complex, it can follow the two-path mechanism. It can follow the solvent path also, or it can follow without solvent path also. But in both paths, the product is similar, and there will be retention in configuration. Okay, so there are different evidence which are in favor of associative mechanism. We'll discuss previously the charge effect also, some other effect also, and this is the conclusion part. And the next most important one thing discussion is that on the redox reactions or electron transfer reactions. So in some complexes or some coordinating complexes, the electron transfer also occurs without breaking of any bond in between the metal ligand. There can be a transfer of electron. Okay, And some reactions previously also we discussed, there will be no electron transfer also. Okay, so mostly electron transfer reactions are possible in case of transition metal complexes. In case of transition metal complexes, that means one coordinating complex will donate one electron towards the another complex. One will be get oxidized, another will be get reduced, like that. And the complex which loses electron. Suppose out of these two complex here, you can say FeCN6 4 minus. That means the oxidation state of iron is +2. Here the oxidation state of iron is +3. Then tell me, in which direction the electron transfer can possible? That means from +2 to +3. That means if this complex, Fe2 complex, it will donate an electron from this part, then it will get converted to Fe3. And here, this complex, if it will accept a pair of electron, this Fe3, it can get converted to Fe2. And the complex will be like that. So the complex which loses electron or the oxidation state of metal increases. Here initially the oxidation state is +2, then after the reaction the oxidation state is +3. It is said to be oxidized. It is said to be oxidized. Which complex is one? This one. And this complex is called a reducing agent. This part will be called as a reducing agent. And the complex which accept electron, this one, it will get converted to this one. Initially Fe+3, finally Fe+2. It will be called as, here reduction occurs, and it will be called as a good oxidizing agent. It can behave just like a oxidizing agent. That means electron transfer always occurs from the reducing agent to oxidizing agent, or I can say electron transfer always occurs from the reductant to oxidant. That means from this complex to this complex. The final product will be this one. So the electron transfer in between the coordination complex, it can occur by two mechanisms. One is outer sphere mechanism, another is inner sphere mechanism. You can see here. So OX means oxidant and RET means reductant or reducing agent, or OX means oxidizing agent. Okay. So in outer sphere mechanism, initially the oxidant and reductant come closer to each other and they will form a precursor complex initially. You can see here. They will form a precursor complex. So these are the steps of outer sphere mechanism. Okay. Initially, they will get closer to each other. They can form a precursor complex. In the second step, there is activation of precursor complex, which includes the reorganization of the solvent molecules. Reorganization of solvent molecules means when an oxidant and a reductant need to come closer each other, there will be some Coulombic force of interaction in between oxidant and the reductant. If the solvent gauge or the solvent atmosphere around every complex, it may be oxidant and reductant, it will be more. Then the formation of this precursor complex, it will be very difficult. It will be very difficult. So the solvent arrangement is also necessary. That means to get closer to each other for oxidant and reductant, it need to come over the solvent interaction along with the metal complex. So in the second step, the precursor complex, we need to make a reorganization of solvent molecules. Because if the more amount of solvent molecules are present on the atmosphere of oxidation, oxidant and the reductant, then definitely they will they will prevent the transfer of electron transfer. They will prevent the electron transfer process. So in second step, the solvent reorganization is necessary, and along with the ml bond length changes also. When they come closer to each other, the metal ligand bond length, it will changes. That means this change is favorable of for transfer of electron. That means one of the electron, it will transfer from one of the reductant to oxidant. So when there will be transfer of electron occurs, there will be definitely change in bond length. Why? You can see here Fe2 plus along with bond with forming a bond with cyanide, and here Fe3 plus forming a bond with cyanide, the same complex. But when the electron transfer occurs, the bond length is now not similar. because the interaction of Fe2 plus with cyanide and the interaction of Fe3 plus with cyanide is different. In case of Fe3 plus, they can easily attract the cyanide, but in case of Fe2 plus cyanide, it cannot easily attract because here the metal charge density is less. So is saying that when the electron transfer occurs, there will definitely changes in ml bond length occurs. That means reductant bond length also changes, oxidant bond length also changes. And after the transfer of electron, one will be getting the positive charge, reductant who donates the electron, and the oxidant who gets the electron, it will be OH minus. And in the final step, the ion pair dissociates to reduction plus and oxidation minus. Okay, then the next step, when you will see the example, you can easily understand. Okay, what are the silent features of the outer sphere mechanism? So the first one is that if the both the reactants, oxidant and reductant, should be kinetically inert. If the both the reactants are kinetically inert, the electron transfer can occur more easily. If suppose one of the complex is labile and another complex is labile, then the inert complex should not possess a donor atom. Okay, it is about the inner sphere mechanism. So whatever it may be, if the two complexes of the reacting side it will be kinetically inert, then definitely the electron pass it will be very very fast and it will be good. But if one is labile, another is inert, okay, then there can also the transfer of electron, but it will be little bit slower. And the postulate saying that if there will be one labile complex, another will be inert complex. In inert part, there will be no presence of donor atom, which can be used to form a bridging ligand. Yes or no? If these two complexes, we can say this is one complex, this is one coordination complex. He's saying that if the first one will be inert and second one will be inert, there will be no issue, there will be transfer of electron. If one will be labile, suppose this complex will be labile, and this second complex, there will be no presence of donor atom, which can act as a bridging ligand. If there will be presence of bridging ligand, they can form a bond with this metal complex. They can form a binuclear complex, just like inner sphere mechanism. And further discussion very well. Okay, you can see here the outer sphere mechanism. It can occur for these two complexes: chromium cyanide 3 plus and iron cyanide 3 plus and chromium water 6 2 plus. If he's saying that if both the oxidant and the reductants are labile, there is a possibility of electron transfer from pi star of reductant to pi star of oxidant. So here actually pi star doesn't mean the anti-bonding orbital. Pi star means particularly he's saying that the two T2G orbital, T2G orbital. Okay, so the reaction proceeds through the outer sphere mechanism. That means here if you say iron water 6 2 plus, so what will be the electronic configuration? If I say iron 2 plus, in iron how many d electrons are present? Particularly d6. Iron is d6. D6 means with the ligand it will form, it is a high spin complex, it will form Tg and Eg. So in T2G the electronic configuration will be 4 and Eg the electronic configuration will be 2. So T2G4 Eg2. These things are you can also previously you can studied in a graduation last year crystal field theory T2G Eg arrangement. So this T2G orbital is favorable for the pi bonding. So this T2G orbital is just represented as a pi star orbital. If I say iron water 6 3 plus, here iron it will behave like also it is also some T2G orbital, it is some Eg orbital. Okay, so he's saying that one of the irons T2G orbital electron it is donated towards the another iron's T2G orbital. That means the transition of electron occur from the pi star orbital or I can say T2G orbital to another iron complexes T2G orbital. Yes or no? So we can say this transition is called pi-pi transition or T2G T2G transition. So particularly the outer sphere complexes, the pi-star transition occurs. That means we can say from T2G orbital of one of the metal complex, the electron will transfer to another metal complex's T2G orbital. Okay, another thing, if both the reactants are inert with respect to the ligand exchange, if I say FeCN6 4 minus, FeCN6 3 minus, these two are inert because in both cases strong ligands are present. Definitely, these two will be inert. A close approach of the metal ion is impossible, and the electron transfer takes place by tunneling. So tunneling means just one of the electron from the T2G orbital, it will easily transfer to another metal complex without making any bond with the metal complex. So the tunneling or electron tunneling through tunneling electron transfer takes place particularly in outer sphere mechanism, not in the inner sphere mechanism. So you can check here some other reactions also. You can check your IGNO study material also. Here you can say this previous one example Fe water 6 2 plus Fe water 6 plus 3. Here in T2G orbital 3, here in T2G orbital 4. The electron will transform from this T2G orbital to this T2G orbital. Okay. So mostly in outer sphere mechanism, the electron transfer will occur from the pi star orbital of one of the metal complex to another complex. That means from Fe, one of the T2G orbital of Fe to another 2T orbital of the Fe star. You can take or discuss another examples. Manganese CN6 3 minus also, manganese CN86 4 minus also. Here the electron will transfer from this manganese to another manganese. Okay, so when the similar types of metal complexes are present, we can say this particularly these types of outer sphere mechanism. We can say this types of reaction is called just like self-exchange reaction. It is following the outer sphere mechanism. If different types of metal complexes are present, here we can see molybdenum and iron. The electron transfer is occurs from this iron to molybdenum. And T2G orbital of iron to T2G orbital of molybdenum. If different types of metal complexes are present, we can say this is a cross reaction. So self-exchange means similar types of metal along with a similar number of ligand is present in between the two metal complexes. If different types of metal complex is present, we can say this is a cross reaction. So in the outer sphere mechanism, neither bond is breaking or neither bond is making. Okay, just electron is passing from one metal complex to another metal complex through tunneling. Okay, so there will be no need of breaking any bond or no need of making any bond. Just electron will pass. Just the two metal complexes come close to each other. One of the electron from Any complex, it will transfer to another complex, and they will form the two product complex like that. Here you can see T2G6 is G0, and another complex FeCN6 4 minus this one, 2 T2G of FeCN6 3 minus. Okay, so this transfer is called, we cannot say T2G transfer, because T2G orbital is responsible for the or carrying the pi symmetry. We can simply say pi star transition. We can say pi star transition. Okay. Another postulate is that in outer sphere mechanism, if the ligands present in between the two metal complexes are the pi acceptable ligands, then it will attract. When there will be presence of pi acceptable ligands, it can easily withdraw or attract the metal electron towards itself, or it can easily withdraw the metal electron of the nearer complex also. Okay, so the presence of a pi acceptor ligand, it will always in support of electron transfer process. So the tunneling or electron transferring process, it will be faster when in metal complexes the pi acceptor ligand is present. So you can take, if you are taking FeCN6 complex and you are taking FeCl6 complex, then definitely in FeCN6 complex the electron transfer process, it will be faster, because cyanide is a biaxial ligand, and it facilitates the electron tunneling process or electron transfer process more easily. Okay, we can see here also T2G3 initial, T2G6 G0, T2G5 G0. Here you are taking another process. Here you are taking a has-been complex and a has-been complex. Previously you are taking in between two low spin complexes. So the arrangement is different. Here, the electron will transform from T2G3 to T2G4. Okay. If Fe3 plus metal complex is present, the bond length will be 78 picometer. And here Fe2 plus, there is a printing mistake. If Fe2 plus is present, the bond length will be 92 picometer. That means along with 2 plus metal complex, it is forming a larger bond or weaker bond. Along with 3 plus oxidation state, it is forming a strong bond, having less bond length. But here the difference is larger. Here the bond length is 79 picometer and the bond length is 92 picometer. In previous case, you can check the bond length is 195 picometer. Here also 192 picometer. Okay. Here the difference is 3 picometer. Here the difference is much more, 14 picometer near about. So here the bond length difference is larger. So when the bond length difference is larger in between 2 plus oxidation state and 3 plus oxidation state, that means the rate of reaction will be definitely slower. So when there will be larger bond length difference, that indicates that the orbital geometry of Fe2 plus and in between Fe3 plus, there will be larger energy gap. There will be larger energy gap. When there will be larger energy gap in between the different orbitals, then the electron transfer, it will be comparatively slower. It will be comparatively slower. So from the bond length data or bond length difference, you can predict that whether the electronic transfer process, it will be slower or faster. Okay. So when there will be larger bond length in these metal complexes, we need more activation energy. We need to put more input energy for the electron transfer favorable, for making this process more favorable. So we can say out of these two processes, this one will be faster, this one will be slower. Here in here we need no activation energy. Here we need activation energy. So this is all about outer sphere mechanism. In the next class, we will further discuss a little bit about the outer sphere mechanism, then inner sphere mechanism. Then we'll go for the bioinorganic chemistry part or energy processes about hemoglobin and myoglobin. We'll discuss about hemoglobin and myoglobin. Okay. If you have any doubt, you can ask. And these things you can get your material also. Okay. In unit 5, electron transfer process reaction and outer sphere reaction. Similar thing, oxidation and oxidant and reductant, it will form the precursor complex, then it will form a activated complex, then it will behave like just like after electron transfer, it will behave just like ion pair. One will be positive, another will be negative. Then this ion pair, it will dissociate to oxidant minus and the reductant plus. The same thing, it is noted in the study material also. You can see. This is the example Fe2 plus and Fe plus 3. Then there will be inner sphere mechanism also. So in next class we will discuss about the inner sphere complex. You can read out also the things written in simple language. Their bond length difference 14 picometer. This indicates that the energy level of the orbitals are not equal. Okay, so energy level of the orbitals are not equal means there is a huge difference in between Fe2 plus orbital energy and Fe3 plus orbital energy. So when there will be electron transfer occurs from Fe2 plus orbital to Fe3 plus orbital, definitely the electron transfer process it will be slower. So because there will be huge difference in energy. So the issue is that here also outer sphere mechanism occurs, electron transfer occurs through tunneling. Here also tunneling occurs. But when these two complexes will be inert, the inert when the two complexes will be inert, the electron transfer process will be very faster. This one. Okay. But here the two complexes are labile. So how can you identify labile and inert? You can check the previous class note also or your study material of unit 1 and unit 2. How can you identify this complex is labile and this complex is inert? In previous class also, I told when the CFE crystal field activation energy is negative, we can say this complex is inert. When the CFE is positive, we can say this complex is labile. Okay, thank you.